I like this problem because it's pretty interesting but also quite challenging. So it says we have these two particles A and B that are moving in two-dimensional space. Particle A is moving along the line y equals 30 meters, and it's moving with a constant velocity of 3 meters per second in the positive x direction. Particle B starts at the origin, and it starts from rest but accelerates at a constant rate of 0.4 meters per second squared in some direction. And the question is, in what direction should particle B be aimed such that the particles collide somewhere? Okay, so to solve this, we're going to need to write down expressions for the x and y positions of these particles as a function of time. For particle A, its horizontal position, I'll call that xa, is going to be equal to simply 3 times t, since it's moving with a constant velocity of 3 meters per second in the x direction, and it starts from x equals 0. The y coordinate is just going to be constant. It's moving along the line y is equal to 30. For particle B, we have accelerated motion from rest, so its position in the x and y directions will look something like 1/2 multiplied by an acceleration multiplied by t squared. So for the x position, we'll have 1/2 multiplied by the x component of the acceleration. And given the way that the angle is labeled in this figure, that should be a times sine theta. The acceleration is given as 0.4, so that'll be 0.4 sine theta t squared, or 0.2 sine theta t squared. The y position will be something similar. That'll be 1/2 multiplied by the acceleration times cosine theta t squared, which is 0.2 cosine theta t squared. Okay, so in order for these objects to collide, they have to have the same x and y position at some time, so we can set the expressions for the x and y positions for the two particles equal to each other. So if we do that, we will get down here 3t is equal to 0.2 sine theta t squared, which will give me sine theta t squared is equal to 15t. And then for the y positions, we'll get 0.2 cosine theta t squared is equal to 30, or cosine theta t squared equals 150. Okay, so we have this system of two equations here in t and theta that we need to solve. So I'm actually going to solve this for t first. Now you might look at this equation here and be inclined to cancel the factor of t before going any further, but I'm actually going to leave them like this, and I'm going to make use of the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So if we square both of these equations and then add them together, I'll have sine squared theta t to the fourth plus cosine squared theta t to the fourth is equal to 15t squared, which is 225t squared, plus 150 squared, which is 22,500. And then when we use the Pythagorean identity, we get t to the fourth is equal to 225t squared plus 22,500. So this equation is solvable if you realize that it is really just a quadratic equation with the variable t squared. So we can make a substitution. Let's say let's x equal t squared. So now we have x squared minus 225x minus 22,500 equals 0. And believe it or not, this actually turns out to factor. 22,500 was 150 squared, so that's also 300 times 75, and 225 happens to be the difference between those two numbers. So this factors to x minus 300 times x plus 75 equals 0. Now x is equal to t squared, so we're going to have to take the square root of x to get our value for t, so x equals 300 is the only solution here that really works. So t is going to be the square root of 300, or 10 times the square root of 30. Okay, so now we have t, so we can finally solve for the angle that we need. I guess we can use either equation here. I can say sine of theta times t equals 15. Now I will cancel the factor of t. So sine of theta is equal to 15 divided by 10 root 3, which is 3 over 2 root 3, or the square root of 3 over 2. And if you remember your unit circle from trig, that should give you an angle theta is equal to 60 degrees. Okay, so looks like we have our answer. We want to aim our particle B at an angle 60 degrees away from the y-axis, and then these two objects should collide at a time 10 times the square root of 3, which is about 17 seconds. So let's check this, put this into Desmos. So here are the equations that we have now for our x and y positions with the values for theta and t that we've solved. And if we run this forward, the particles should collide at the very end. And there you go. All right, thank you for watching.